Beautiful. How are you? Okay, so we started this topic the last class. We were discussing the issue of waves and sound. I remember I said a wave is a disturbance which travels through a medium and transfer energy from one point to another without permanently disturbing or causing any permanent displacement of the medium itself. So I've decided to actually display material to be able to give you all that we have discussed. I remember I told you about when you drop a stone in water. I remember I told you that there is something called transverse wave, electromagnetic waves, longitudinal wave, and mechanical waves. All right. I remember I told you that when a wave requires a material medium for its propagation, it is called magnetic waves. If a wave does not require a material medium for its propagation, you call it electromagnetic waves. And then now, in terms of direction, if the direction of movement of the medium is perpendicular to that of vibration of or the movement of wave, you call it transverse. If they both have the same parallel direction, you call it longitudinal. So that is all the explanation you have there. I told you about crest, trough, and I told you about wavelength. I knew I was discussing that wavelength thing with you. And then the characteristics of wave, I think those are the ones that I did not conclude on last week. Okay. I discussed the issue of amplitude and trough. So let me quickly show you this diagram. This diagram was drawn for you last week. I can remember vividly, last class, that the maximum displacement from the medium position is called crest, while the maximum displacement, downward displacement, is called trough. So you have it there. And then amplitude is actually the mean displacement from the medium position. Lambda, which is the wavelength, I said it is the distance between two crests or distance between two troughs in a particular wave. And then you have the frequency is the number of complete vibration or oscillation. Period is the time required to complete all those definitions. See, in physics, it is both definition and calculation. All right. Mathematics, nobody will ask you what is statistics, define sequence, define logarithm, or define indices. They don't ask that in mathematics. It's purely calculation. But when you come to physics, they will ask you to define those concepts. They will ask you to state laws. They will ask you to interpret data that is given, and they will still ask you to do calculations. So if you are very good in physics, it will show in your mathematical prowess. So it is both definition and calculation. That's just the big deal there. So don't just focus on calculation. You have to also learn definitions. And that is why all these things are very important. And I want to believe you have text materials that you can make use of. And if you need any portion of this, you can just tell me to wait for you while you screen grab, while you screenshot anyone that is convenient for you. But it is until you mention it. If you don't mention, I will just move at the usual pace. And I'm loving this. There is what we call equation of wave. This is what you are seeing on equation 11.1. It is called equation of wave. A sine 2 pi over lambda into brackets VTX, or you can call it, let me just make it more clearer to you here. Please, you need to write this down. This is a mathematical representation of this graph. If they ask you to represent this graph you are seeing, in a mathematical, when a wave is moving in a particular direction called the x-axis, the movement of that wave at any particular time t. Very important. Okay, so having done that, we have all of this. Frequency is related to period by velocity is over t, but because your f is t, so you can write it as f lambda. The velocity of a wave is f lambda, v equals f lambda. V equals f lambda. You can use it to determine a lot of things. Go to properties of wave. How does it behave? When you see or when you experience, what can you say you see? Just like when you see a human being, you know that this is a human being. When you see an animal, you know. So when you are experiencing a wave situation, what are the things you can say a wave can do or cannot do? So these are the phenomena you observe. All known waves undergo the phenomenon of reflection, refraction, diffraction, and interference. All right. There is also what we call polarization. But that polarization is only experienced by transverse wave. Longitudinal wave don't experience polarization. And that is why it is not included here yet, because everything, we want to talk about something that is, common to all of the waves before we now begin to section it. Which one can longitudinal wave perform? Which one can transverse wave perform? Which one can electromagnetic wave perform? Which one can mechanical wave perform? So let's talk about reflection. Just like you have a mirror, any ray of light that hits a mirror will be reflected back. And that is why you are able to see yourself when you look in the mirror. Waves can also be reflected. Waves can also be reflected. If you stand in a empty room and you say, oh, the four walls of that room will receive that. And then they will send this when you hear yourself. An example of reflection of wave is sorry for that. A call disrupted my uh, okay, so where are we? I believe everybody is still following. Hello. Let me be sure I'm still connected. Okay, I am. Thank you. All right. Okay, I can see. I can see. So let me just still continue with the class so that we won't have to break all of a sudden. Okay, here am I. So I have said all waves undergo reflection. Reflection is when a wave is sent back to the source from a particular point, and it requires the hard surface to be able to send back such reflection. This reflection of wave, especially in sound, has a very great application. It has a very great application. We can use reflection of wave to determine the distance or the depth of the seabed. A very gigantic ship, they will send heavy sound through the water, and the sound will go through the water and hit the hard part of the sea floor. And then the sea floor will reflect the sound back. And once they are able, they will time the time, they will time it. As at the time they receive the reflection, they will calculate, they know the speed of sound in water. They will be able to calculate and get the exact distance of the seabed from the water table or from the surface of the sea, as the case may be. So there's a lot of it that you need to know. What is refraction? When there is a change in wavelength, the wavelength, the speed of refraction. An example of refraction is when you put a stick inside a glass of water. Look at the stick. The long stick is straight. But when you put it inside a glass of water, it will appear bent. It will look like that stick has bent. You can try this. All these are simple experiments that you don't need a big laboratory to set up. They are big experiment. I mean, they are small experiment. You don't need a big laboratory. Just pour inside your glass cup of water, transparent glass cup of water. You can call it a water beaker or something. Put water inside it, let it be full. Take a straight ruler, put it inside and look from the side of the glass. You are holding half of the ruler on your hand, taking the water at the same time to see whether this ruler has entered the water halfway. You will notice that some part of the ruler looks like it's bent when it enters water. That's what we call refraction. All right, that's what we call refraction. Refraction helps us in lenses. Lens. So I've talked about reflection. I've talked about refraction. When opposed, you cannot enter directly. You have to bend. You have to bend before you can enter such place. Maybe the dog house, you just want to pick something, you just want to do something inside your dog house, you want to clean it or something. You cannot enter straight because the post of that door is not like your normal house. So you have to bend down to be able to see what's inside. So that's the way diffraction occurs. When a wave is traveling and it encounters a barrier, there is a way to bend around the obstacle to be able to continue its journey. So that behavior is called diffraction. It's called diffraction. Okay, you see diffraction in prisms. Yeah, glass prisms. That's diffraction. Light, and then you put a glass prism across the ray of white light, you will experience what I call rainbow because it will split the white color into several other colors. That's what we call the rainbow experiment. All these things, if you have a glass prism, you can try it. Then we have what we call interference. Interference is when two waves combine together. Okay, the combination of wave is also called superposition. When two or more waves combine together, we call it superposition. And this interference, we have two types. We have what we call destructive, and we have what we call constructive. A destructive interference, I'll give you very practical situation around all these things that you need to know. Let's assume we have two people that are singing, all right? And when you combine the two voices, there are some people when they combine together to sing, you will enjoy the song because of the way the nature of the sound is combined together. That one is called constructive. But when someone is your mood, that one is called destructive. Right? So all these things are what you can. I'm just talking about one aspect which is in sound. There are also aspects because sound is not the only example of wave. We talk about electromagnetic all these things like all this theory. You can combination of colors in physics. We have combination of colors, but we have combination of light. All right. Yellow light plus blue light is not going to give you the same color that yellow color paint plus blue color paint will give you. If you are interested, go and find out. Go online and check all these things. They are real. And if you so much love physics, you will understand that physics is a very interesting thing. Now, let's talk about polarization. I told you earlier that not all waves can be polarized. Maybe you were not listening, but hear it again now. Not all waves can be polarized. The only wave that can be polarized is called transverse wave. They can ask jam. Jam has a way of asking simple questions that can confuse you. The only wave that can be polarized is the transverse wave. And you can see it, they stated it in a transverse wave, such as light. The vibration can be in any direction perpendicular to the direction of wave motion. It has to be a perpendicular. So when you have it at a perpendicular, that's what we call polarization. See? And you have it here, direction of wave motion is here, the vibration in this, and then now we are changing the direction of the vibration, in one direction only. You have it like this. This is an unpolarized light. You can see the waves going different way, but this is a polarized light. They use this experiment. There are some, we call them laser beam. When they, this is one thing I've seen, okay? A very close relative one time ago, sometimes ago, had this growth on his hand, and they've they've done operation, they removed it like 3 times and it kept growing back. When they remove it, it will grow back. When they remove it, it will grow back. So somebody now advised them that they should go to UCH, that's the University College Ibadan. That's the teaching hospital of University of Ibadan. So it was a stem cell to kill that growth, that cell that is causing that thing. So they will just put it and they will direct that light into that part. They have all those equipment. They will direct that light into that part of it and it will hit it. It's not like it is hot. It's not like your hand will be burning. But very scintillating experiment. When the man was relating his experiment, and within 3 weeks, this thing stopped growing. So there are a lot of that thing you need to know. Now, so we have what we call stationary wave. I don't want to sound too excited about it. Before I continue, let me check how many more minutes we have so that we don't. Okay, good. We still have about 20 minutes, so we can quickly go around it. So these are the explanatory aspects of waves before we go into calculation. What is a standing wave? A standing wave is a wave that has an origin and a terminating point. It has an origin and a terminating point. Let me use that word. You can see in this figure here, there is this end, there is this end. So the wave is not going anywhere. It will just be going, it's like a stagnant water. It's not flowing anywhere. All right, it's just there. So anytime you disturb it, it's like you put the water inside a bath or inside a big container and you trouble it. All the trouble will be inside that container. It's not that it will spill over and start rushing elsewhere. You have it here. So you can call it a standing wave, you can call it a stationary wave, all right? So this is what we call stationary wave. And it says that if two identical sets of waves traveling in opposite direction, so I think at this point I will need to do some. So you have something like this. This one is going this way, and this one is going this way. Okay. So you have this, you have this, you have this, and then this, you have this. Let me use blue marker now. You have this, you have this, you have this. At the end of the day, by law of reflection, once it gets here, this one will turn back this way. All right. going this way, you see that both of them are just points. So we call them standing waves or stationary waves. That's what we call them. Okay, stand or stationary waves. Now, based on that, let's quickly talk about the wave of sound, propagation, production of sound. What are applications? This, e.g., guitar, string, a drum, surface, any vibrating body will produce a sound. Your diaphragm, your sound that you are able to hear me, that I'm producing a sound. Go and check my chest. You will see that it is relaxing and contrasting. I have what I call diaphragm. The sound box in my body is actually vibrating. My throat, sound, what do you call it? Sound pipe. Yeah, my sound pipe is also contrasting and relaxing. Any parts or any objects that can vibrate will produce sound. And I need you to know that when you are cooking, when your water boils, what do you notice? The heat that is boiling your water is not even making sound, so to say, but the water will be doing, you can see the bubbling of water is producing sound because those bubbling are moving up and down. The molecules are moving up and down. So for any object to vibrate, the molecules of that object must be experiencing some motion, some movement. That is why they are vibrating. All right. And in the course of vibration, of course, sound is produced. So you need to know that. And, an example of body that vibrates easily are just the ones they talked about here: guitar string, drum surface, even your wall. When you slap your wall, it will produce sound, pa, because there is a vibration. All right. So the to and fro motion of vibrating body set air particles next to it into vibration. This produces region of compressed air. You can decide to screenshot this. These are good key point notes that you need to know. Sound is a mechanical wave because it requires a material medium for its vibration. Okay. Waves can only be propagated in material medium, and it is known as mechanical waves. They also talked about all of this. Let's talk about speed of sound. Let's talk about speed of sound. Sound travels fastest in solid. The fastest mode of travel of sound is observed in solid. The speed decreases when it enters into a liquid medium and travels the slowest in gas. Let me come again. Speed of sound in solid objects is the highest. Liquid object is medium. Gaseous medium is the lowest. Yeah. And you will notice that by what they give you here. The speed of sound in here is about 330 meters per second. But when that sound enters into water, 330, it becomes 1,500 meters per second. When that same sound enters into a steel, it moves as fast as 5,000 meters per second. Yeah. So you have learned that. Okay. Let's go to reflection of sound. I've told you how can be made use of. Sound is being reflected. I think we have some destructive superposition there. There is a sound below that is giving us concern. If your mic is on, can you help us mute it? Ola, please. your mic. So let's just still continue. Please, in case you have anything to say, you can send it as chat. I've not seen anybody ask any questions since. Or maybe I'm the one that is not reading chats. Nothing is coming up in my chat, so nobody has spoken yet. It's fine. Okay. So we talked about reflection of sound. Sound can be reflected because it's a wave. Every wave can be reflected. Every wave. And the reflection is more observable phenomenon. In sound, I've told you that they can use the application of that reflection of sound to determine the depth of the seabed. All right. So this is the formula. And I'm going to show you why it is this formula. You know, when you have a distance, let's say a human being is standing like this, there is a wall standing like this. When you produce a sound from here, it travels to and is reflected back. So the distance is D here, and then the distance, same distance is D, because it will first go and then it will come back. So that is why you have 2D. Total distance cover over time taken. The same way you learn it under motion. Distance cover over time taken. But in this case, this object here, nobody can measure when the sound came here. But because it will reflect it back, you can measure the time you release the sound and the time it comes back to you. So the total distance cover will be the distance from your end to the wall and then back to you. So you have to multiply that distance by 2, and that is what you are seeing here. 2D over T, the time taken to travel. I've said that people on the ship, when they send a sound down the seabed, they wait for that sound to come back to them. So you can use that to determine the distance covered, because you know the speed of sound in water, you know the time it takes, so you can use that to determine your distance. All right. So we discussed this. Okay, I can take this out now. I can take this out. All right. Interference of sound are combined together. How do you know? This is called beats. Or, frequency is measured in hertz. You talk about the quality of sound, pitch, intensity. Pitch and intensity is a measure of the depth of its tone. The way I'm talking now, this is the tone. And if I say like this, it's also a tone. The frequency at which I'm talking now is quite different from the frequency at which I'll be talking now. So sound, there's a way you can vary your sound and it will convey different message, but not even after that. We are just after the pitch. There are some people when they talk, their voice is more cool, more sonorous than the way I'm talking. I'm a man. And there are some men when they talk, you think they are women because of the pitch. Some people can sing at a very low pitch. Some people can take it high there. So even as a student of physics, there are some things you need to know about sound, music, intensity. A deep low pitch sound has low frequency, while a shrill high pitch sound has a high frequency. Okay. Woman here is capable of detecting sound waves of frequency ranging from 20 hertz to 20,000 hertz. And I want to tell you something. There is what we call ultrasonic sound. Ultrasonic sound. There are some sounds you cannot hear as human beings, but some animals can hear it. Animals like birds, dogs, they can hear ultrasonic sound. Do you know that they have also devised, even your Android phone has it. I could remember years back when I started using Android phone, there's what we call mosquito repellent sound. You may not even hear it if you are that a lousy person. It will be sounding like a mosquito sound, but it's keeping mosquito away. So if you have that kind of sound, you can set it on in your phone. Go to Google Play Store and see mosquito repelling sound. It will bring different apps that have that sound to you. If you want to sleep and you don't want to be disturbed, you don't have money for insecticide, but you have a Android phone, you can set those sound. That's application. The sound will keep mosquito away. I don't know, that's just one of those wonders of physics. Yeah, the sound will keep mosquito away. In fact, it has been known that even sound can kill rats. When they set some sound frequency, because the ears of rats very soft, so it can pick very soft sound. So if you blow some sound in your area, especially party places where it is always very boom boom, rats cannot withstand them. So there are some frequency of sound that can kill rats. And even as human beings, they've told you, don't always listen to loud music. Those of you that will always put on earpiece, listen to loud, it can destroy your ear. Okay, then let's talk about vibrating strings. And in this place, we are going to be doing a bit of calculation. And this is application of standing waves. Vibrating string has this formula, 1 over 2L square root T over N. What is T? The tension in the wire. There are some wire, when you plug them, they give you sound. And you know you are applying a force. The force is actually equal to the tension. Ah, wow. Then the M, mass of the wire, all right? And look at this. So here you have, from here to here, you have the lambda is half. The lambda is half here. Here, let me call this one A. In A, of course, the lambda is half. In B, the lambda is 1. The length of the
Excuse me, sir.
length,
I asked
yes,
a
go ahead.
question in the chat. You don't respond to my question, sir.
Oh, good, because I'm focusing on let me quickly go to that. Let me see. Let me pick the question. Sir, what of node and antinode? Yeah, okay. So let's quickly go there. This is where you talk about node and antinode. Here, this is it. Exactly here is where you have node and antinode. So your antinode is just like your, maximum height that your displaced, this is antinode here, A. The node is when you reach this point. You can also refer to this part as your node. While you refer this, this part, sorry. You can also, okay, I want to clean this. I don't know why it's not cleaning. Okay, so here is antinode, here is node. You can also refer to this part as your antinode. This now tell you this is what happened. Let me quickly use this. Let me use this. So I'm taking this away and I'm coming back here. I'll go back to that. What's the time? Okay, we have about 4 minutes left. Let me do this. Where is it? Okay. So this is what we need to know. I need you to pay attention to this. When you have this, the length remains the same. L remains the same. But what you need to note now is the lambda. Lambda is what? What is lambda? Wavelength. Here, I've discussed that your wavelength is the distance between two troughs or distance between two crests. So from here, let me use another color now. From here, this is a wavelength. So if this length remains and this place to this place is a wavelength, then I can also assume that from here to here is half. So this is half. So the whole of this, L is equal to half of my wavelength. L is equal to half of my wavelength, half lambda. But in this place now, my L is equal to lambda because I've been able to complete a cycle from here, another side, starting another journey. So this is lambda. So when you have something like this now, I'll go back to that book. When you have something like this, you have something like this. Come back. You have something like this. Your L now become 1 lambda plus half lambda. And then this one gives you what? 3/2 lambda. All these calculations, I want to go from here. The behavior of wave is changing the world down this. So that next class we'll be discussing some interesting calculation. At least today we've been able to learn some basic things. Yes. So let's go back to the book now. So